My name is Federico Campoli, not Campoli. And today I will talk about ZFS with PostgreSQL. A few words about myself. I look younger, but I was born in 1972, so this year I will turn 52. I started with the IT in 1985, and I discovered PostgreSQL in 2006 after being an Oracle DBA. So I've been stamped in fire with Oracle, and then I stamped myself to PostgreSQL with this, a tattoo with PostgreSQL, and recently I've also had FreeBSD because I love FreeBSD as well. Because Postgres basically was born on FreeBSD. He was born at Berkeley. He's more FreeBSD-like than Linux, despite the fact that he works a lot on Linux. But we will talk about Linux today. And I'm proud member of PostgreSQL Europe. PostgreSQL Europe is the association caring about PostgreSQL within the European Union and the European continental thing. So also the UK, that is no longer in the EU, is part of PostgreSQL EU. If you want to look about it, please click on the link and possibly join the association. So, and I'm freelance DBA. So basically, if you need any help with your databases, on my LinkedIn, I state myself as a spiritual counselor for sad elephants, because PostgreSQL mascot is an elephant after all. And those are some contacts for getting in touch with me. LinkedIn, GitHub, where I host most of my project. I've also prepared the repository for the experiments presented in these slides. Still working on it, so I haven't shared yet the repository. This is my SoundCloud. I am a amateur jazz guitarist. So if you want to listen to my music, is here, and my blog about PostgreSQL is here. Now, let's talk about the ZFS and everything. I will start with a disclaimer. This talk is based on real-life experience. A couple of years ago, I had this customer with this thing that required the experiment with ZFS, and I was incredibly surprised how fast can go ZFS. The tests I will present are just reenactments, because I cannot share real-life numbers, because I'm under NDA. And there are a lot of topics not covered by this talk. We have 27 minutes now and still going. I will leave 5 minutes for the questions. And always test before going in production. This should be paramount. Do not assume that everything is the truth. Things may apply differently to your case. And if you want to share the feedback, I will leave this for a while. Please scan this QR code. I will show also at the end of the presentation. Go on it, because this is a completely new talk, so I need feedback for improving it, because things may not be completely correct. So, table of contents. I will give you some context, pretty funny story, rapid story. The key master and gatekeeper, so our friends PostgreSQL and Linux, how can they summon Gozer after all? Some tests, and wrap up with the test consideration and other stuff about ZFS. So, story is about to hear is true. The names have been changed to protect the innocent, of course. So, long time ago, there was this startup. Was a long time ago, a couple of years ago. The startup had a Postgres running on someone else's computer, the cloud. And this computer was misused and abused by the developers, as usual. And they blamed the Postgres, after all. If you are in doubt, just blame the database, right? And the database ended up completely bloated. So they called the DBA, me, and other guys, but in that case it was just me, that we DBA have a bad reputation of being grumpy, aggressive, and basically Spartans. Well, This is exactly what we did. A lot of tests, and one of these tests was just discussing about ZFS. But before talking about ZFS, why the problem with Linux and Postgres? Well, Postgres and Linux, when I deliver training, I always say Postgres and Linux are not friends. There is a reason for that, because Postgres is multiprocessing. The block size of Postgres is 8K, is one big shared memory segment, the shared buffer, and it consumes a lot of memory. So this, from the perspective of the gatekeeper, Linux, is bad, because Linux uses NUMA, memory pages scattered across the RAM, so not uniform memory allocation. Also, on x86, the block size is just 4K, so it means each page block in Postgres is consuming 2 pages on the Linux file system. That's the reason why, for example, Aurora is using ARM instead of x86. Because in ARM, you can set the block size for the file system to a larger than 4K. This is not possible on x86. Another problem that usually, well, database is frozen, we have a lot of log contention. Wrong thing is Linux that is blocking things because you are consuming just your memory. And Linux, when it flushes the blocks on disk using the synchronous flush, it blocks any I/O. But it can be misinterpreted as a problem with the database. And this is what I prefer. The OEM killer, out-of-memory killer, is the problem. So how many of you have seen Postgres process terminated by OEM killer because out-of-memory? And what happens? I'm seeing somebody saying yes. What happens when this happens? Postgres performs a crash recovery with all the bad that will happen related with the crash recovery. So Linux is definitely not optimized for running PostgreSQL. But they can be pushed together and summon Gozer to get a powerful operating system running with a powerful database management system. How can you set this thing? Tune the max connections, enable the huge pages, so literally do not scatter the memory across the RAM, just stick everything into one huge segment. Do not oversize the shared buffer. This is another point I will come back at the end of the presentation, why this thing is very critical. It's not like MySQL where you can set all the memory. Postgres, it works much better with a smaller shared buffer. Not so small, but not so big. In Linux, you can do exactly the same thing for optimizing it. Disable the NUMA balancing, configure and use the user pages, because you need to tell the kernel to use huge pages in memory. Otherwise, Postgres won't use them. Configure correctly the VM dirty ratio, so avoid the risk of having synchronous flush on disk, and disable the memory overcommit, because the memory overcommit from a database management system point of view is a bug, so do not use it at all. Then we come to the file system. Oh yeah, on supported architecture, set the file system block to 8K. Or use a file system more flexible, like ZFS. But ZFS, it comes with a cost, and we will see in the next slides. But before doing that, because I need to do a comparison between the ZFS and a native file system, in that case I use the XT4, let's see how much we can optimize the XT4. In XT4, we have the defaults that are definitely not optimal for running with a database system. Because the default says, update the access time for files every time you touch the files. And because Postgres touches a lot of files at any time, you will get a lot of extra work in terms of CPU that is not really needed. So you need to disable the access time. You also can just disable the access time for directories only. Normally, the setting is no A time, no dir A time. That's it. Barrier set to 0 also disables the write barriers for mount point, but as for Red Hat papers, disabling this thing on virtual machines is not recommended because there is a real disk on the underlying that may act differently from the virtual disk. So normally in this experiment, in these tests, I haven't set the barrier to 0. But you can set the data write back journaling to increase the performance in writes. But we also have ZFS, the subject of this talk. ZFS is described, this is copied entirely from the wiki on Arch Linux, so shamelessly copied from that. So it's the last word in file system. It's stable, fast, secure, future-proof. It comes with pooled storage, copy on write, snapshots, data integrity with automatic repair, RAID-Z, and a maximum size for files and the number of limit for number of files ginormous. When I first discovered ZFS, I thought, this is not a file system. This is a database. And the jargon in ZFS is very similar to the databases. We are not talking about mount points. We are talking about data sets. And we are not talking about the block size. We are talking about record size. So for a DBA like me, that's fantastic. I can work on top a database on top of another database. And this thing may work very good. Well, not exactly. I had a lot of pushback from this thing. The problem with ZFS on Linux is it comes with initially from the license. The CCDL is not compatible with the GPL, so you won't find ZFS in your normal Linux distribution. You have to install separately, and you have to run ZFS as a module. Differently from FreeBSD, you get ZFS out of the box. Is memory greedy. You need a lot of memory for making run this thing. Linux normally works with a Linux kernel cache in tandem with the programs. But ZFS uses a completely different caching method that it uses it has to be configured and usurps memory to the Linux. So for having good caching performance, you need to be sure that you have enough memory for running your Linux, but also for running your ZFS. The maintenance requires attention. As I said, it's more similar to a database rather a file system. So if you ignore the maintenance duties, you will get into trouble. The performance will degrade very, very quickly. So resilvering, scrubbing is something you have to do regularly. Is not very efficient in writes. In particular, because the writes in ZFS are basically transactional, they comes with a similar WAL. This doesn't bode very well with the writes efficiency. So in writes is the Achilles heel, is the weak spot, but it can be circumvented. And there is also some bugs. This is the last one. Is a very horrible bug in the 2.2.0. When you enable the block clone, you will end up with empty blocks. Very bad situation. So enabling the data checksums on Postgres is always a good thing. But the good thing about ZFS is that it comes with a lot of options on ZFS and the module itself, and they are basically, almost everything is dynamic. So you don't need to remount your file system, you just need to write the new options, and the new option will apply to the newly written data. The existing one will not get the new things. But so you can disable the A-time, similarly to our friend XT4. We can change dynamically the record size. The default is 128 kilobytes, but we can, for example, set to 8K for matching our Postgres block size. It supports transparent compression. The default is gzip, but also supports LZ4, ZSTD. Which one is the best? Depends on the data you store on your system. Postgres internally uses LZ4, so probably, I tested that LZ4 works the best with the Postgres file system, with the Postgres data files. And the log bias, so it can be added a log for generating the intention of access onto the data, can be set to latency or throughput. The default is latency to ensure a minimal latency access. Also, we have the possibility to change the ZFS module. Did I mention that this is basically a module? And it can be set as a module option or can be set as directly into the sys file system, changing the module dynamically without the need of unloading and reloading the module. Obviously, if you set the parameters into the module, you will get the options preserved across the reboots. So it's a very good way to test your stuff. When you are fine, store into the module option, and then you are good to go. So let's check some tests. I recreated the environment at the customer. Yeah, back in the day, I'm old enough to say that thing. So when I started with my first PC, I had 4 megabytes of RAM, and it was huge from my point of view. So, but we had only 640 kilobytes. So the system I used is based on GCP. I created a system on GCP based on Rocky Linux 9.3 with 4 SSD persistent disks, and each disk has been configured for a particular purpose. The hardware, because it's still a virtual machine, used is a E2 IMM8. I didn't push the boundaries. I used a general purpose machine. And with 8 CPUs, 62 gigabytes installed RAM. For my tests, it was more than sufficient. 8 processors, separate volume for WAL area and data area. So I used a separate disk just for the WAL. So in that way, it won't interfere with the I/O with the other disks. And same for the data area, it was a very small one. The minimum size from Google is 11 gigabytes. So I had to create at least a volume of 11 gigabytes for these disks. The XT table space, it was on a dedicated persistent disk, no LVM in place. And ZFS table space, similarly, on the persistent disk SSD. So basically, I created a Z pool on this device, and then I created a dataset on this device with the mount point set for the table space in Postgres, because Postgres supports also the table spaces. Very handy. And into my Postgres, I created 2 databases, one with the default table space on XT4, and another one on the default table space on ZFS. So simple as that. I run the tests on different databases, and I've written my data in different places. Very, very simple to set that. And the ZIL, the ZFS intention log on another persistent SSD disk. No swap area in that case. After doing that, I used Rocky Linux release 9.3, the resurrected CentOS into the new project. I really like Rocky. It's a very nice one, a very nice distribution. The kernel configuration. Did I mention about the settings and all the stuff? So what I did in terms of kernel configuration, I set up the dirty background ratio to 5. That means trigger a background flash, not blocking. Background flash means not blocking flash when the kernel cache contains 5% of dirty buffers. And use the blocking flash only when the kernel cache is full of dirty buffer to 99%. So reduce at the minimum the risk of having a freezing onto my machine in terms of I/O. Because this is one of the classical things the customers come to me and say, oh, I have this database is blocking at any time. I have a locking contention. And then I look at the shared buffer, I look at these settings, I say, no, you are the shared buffer that is generating too much stuff into the kernel cache. And this is the reason why. The Linux stops accepting I/O until it flashes everything on disk. So I reduced the risk to the maximum possibilities. Disable the overcommit memory and set overcommit ratio to 100. So entirely disable the OMM killer. So the risk of having the my Postgres process killed is removed. And then disable entirely the swappiness. Set to 0 because there is no swap. If you set to 1, Linux will expect that there is still a swap, even if it's very unlikely that will be used. Setting to 0 means disable the swap configuration. Postgres 16.2, the last bug fix version, the last major version. Shared buffer set to 1 gigabyte. I have 62 gigabytes of RAM, and I'm just setting 1 gigabyte of shared buffer because the Postgres is not efficient in managing files. Postgres is designed for managing blocks. And because if you set the shared buffer too big, you will have a lot of scattered blocks that do not belong to the exact files. You will consume kernel cache that is far more efficient in caching the files. So having a smaller shared buffer and a large kernel cache, it works far, far better than having a very large shared buffer, because the kernel cache will cache the entire files, and then it will serve the blocks much faster than reading from the disk. So this is one of the tricks for having efficient I/O in Postgres. Workmem 400 megabytes, designed on the memory settings. Max connection, the default, 100. Max wall size, 5 gigabytes, to reduce the risk of having frequent checkpoints during the intensive I/O. And then let's come to PG Bench. I used the benchmark tool. I used the standard transaction type, TPC-B, sort of it, with a scaling factor 500. The scaling factor 500, it means that the tables created by PG Bench are increased by 500 folds the original size. So I have an account table of 50 million rows, PG Bench branches 500 rows, and PG Bench tells us 50,000 rows, 5,000 rows, sorry. Number of clients for the connection, 50. The number of threads working for not overloading, not consuming too much CPU, just 1. Duration, 120 seconds each test. No foreign keys, because I'm interested in throughput. And PG Bench initialization for each test. So drop and recreate the table every time I run a new test. So I will start with fresh files, fresh caching files directly from the disk. Let's start with XT4. XT4 default settings initialization. It takes about 85 seconds for initializing my tables and consumes about 7.4 gigabytes. These numbers are quite similar when discussing about ZFS and ZFS without the compression. So it consumes maybe a little more because the size of the block is slightly bigger. The run is quite interesting because it already runs at 4,900 transactions per second. But remounting the XT4 with no A time, no DRA time, the load time is slightly bigger. I suspect there was something happening on the underlying physical disk. But the run with the no A time, no DRA time jumped in terms of TP transaction per second, and also the latency lowered. So 5,300 transactions per second. And adding the data right back adds also another little jump in terms of transaction per second. So we have a pretty good situation, even without optimization. Now let's see ZFS. The load time is not so bad, honestly. The space used is still 7.4 gigabytes, but with no tuning, well, 1,700 transactions per second. What the hell? It's highly disappointing. It's impossible to, it's very bad. So how do we improve this thing? So even without the entire optimization, we are in a very, very bad situation. So let's start with some optimization. Let's turn the A time off. This is something we will do dynamically with ZFS set A time equal off, followed by the dataset name, very simple. We rerun the initialization, and this time there is a slight improvement. 1800 transactions per second. So removing the access time improves a little, but not so much. It's still what the hell. It's still in a very bad situation. The XT4 with no optimization, we have 4900s. We are, well, slightly better than the half, but definitely not to be used in production. So let's add the compression. I want to shoot in my foot. I say, let's add the compression. Let's kill the CPU, right? So after adding the LZ4 compression, the space dropped to less than 1 gig. And this is a very interesting thing. If you have expensive disks, you can save a lot of money by just using the compression. But the good thing is also the transaction per second improved. And I have a theory about that. ZFS is not efficient in writing. The tests are very write intensive. So writing less data, even if it's consuming CPU clock, it makes the thing work much smoother than going directly onto the file system. There is another test I haven't put into the slides where I set the record size to the size of the Postgres block, and the performance are even worse than the default, because it writes a lot of single blocks that consume a lot of stuff into the ZFS logic. So we have a very good improvement compared to the previous one, but also we save a lot of space. But let's do another optimization, because 128 kilobytes is still too much. It comes with a lot of overhead that may be not optimal for our situation. So after some tries, and there's also some documentation saying, oh, let's put the record size to 16K, the space is no longer under the gigabyte, it's 2.2 gigabytes. But performance is even better than XT4. That's an amazing thing. Honestly, at the customer, we didn't add this performance. We used a different cloud, we used a different file system, different size also for the test. The scale factory wasn't 500, it was 2000. So a lot of more data, but we almost reached the same performance of an XT4 optimized. So the numbers in this case may lie, but the difference is not so big. But the good thing is still compression. You get good performance, and also you get good compression in place. But let's go slightly further for the optimization. Let's optimize the ZFS module. Did I mention about the caching system? ZFS, for caching, it doesn't use the kernel cache. It uses the ARC cache. It's an internal cache. It stands for Adaptive Replacement Cache. If you leave the default, the Adaptive Replacement Cache, it gets resized dynamically by the request of ZFS. And this is consuming time and CPU clocks for operating this thing. So setting to a standard value that you expect it has to be used at most by your application is a very good idea to leave ZFS in free to work on the files and not onto the resizing of memory. Also prefetching, no cache flash, and also the timeout for the transaction when flashing the blocks on disk is critical for this thing. And also, I've added the ZAL intention to ZPool. So I added another device for storing the intention log for ZFS. So it's a way for telling ZFS what is the trend for the access of data at physical level. So the ZIL will drive the pre-caching of ZFS. So, but it was quite a disappointment because the performance, after adding all this optimization, it was slightly worse than before. I think I didn't test the ENOG. I ran this test last Sunday, unfortunately. So I couldn't spend enough time on testing this thing. But what I would expect with this situation, that increasing the scale factor for PG Bench this last configuration will keep it up with the performance. Meanwhile, the previous one without the optimization will slowly degrade. But in any case, at the moment, we have similar performance. It's very, very minimal, the difference between the two. So just to recap the situation, space usage comparison. The best is with LZ4 and default setting. You get the best compression in place, but not the best load time and not the best latency. The best latency you get with Postgres, because with Postgres we are talking about, you get with 16 kilobytes with the record size. And also the same for the transaction per second. The best transaction per second with ZFS is achieved with the record size 16 kilobytes. So now let's wrap it up. ZFS can achieve good performance despite the bad reputation. You have to work on it. Beware of any weird bug appearing. I remember to you this thing. Use the latest version. 2.2.1 disables the option that will cause the corruption bug. They are still working on it. Apparently, it's a bug that has been there for about 10 years. And nobody noticed it because nobody is using the block cloning. Then they added the block cloning as a default. The principle of least astonishment is no longer the case, unfortunately. And this caused a lot of problems when people upgraded ZFS. Always use PostgreSQL with block checksums. So if you have corruption at block level, you will catch at database level. So always enable this thing. And use the tool for your needs. Don't use ZFS if you have a 20 megabyte database. Put it onto a normal file system. It's like the classic cannon to shoot the pigeons, right? And always RTFM. And remember that your mileage may vary. So for the, I also added the translation. No airbags. We die as heroes. I catch this panda in near my hometown, and I'm still killing myself by logging because it's amazing. I think it's the best car even produced by Fiat, the Panda. So I remember you about the feedback about this talk, and that's all. Any question?
Raise a hand. We still have 60 seconds for a very quick one. You can do it, 60 seconds. Okay, I think I check it online. If there is anything, remember, you can click QA and we read your question from the live streaming. No one?
Okay, if you want any question or anything, just grab me and we'll be happy
around.
to talk. Yeah, I will be around in any case.
Okay, great talk from my side, very rich of technical details that I love and from practice that comes from real work. Okay, but you have to be really fast, really fast.
What sites should the database be in order to so you suggest to use this type of optimization?
Well, I will consider a database as big, and for big I mean starting from 1 terabyte ongoing. So smaller databases probably will work much better on XFS. Probably should be the first choice with a lot of drawbacks as well. XT4 for smaller databases, so around up to 300 or 400 gigabytes. XT4 larger at XFS, and then ongoing if you really need ZFS. Welcome. Cool.
Good. Thank you again.
Thank you very much.